Well, I'm calling this a Jamboard, but it really isn't. It's really a Google Doc that I'm just taking notes over. But I like the name Jamboard, so there it is. This first image comes out of your textbook, and it really connects to what students would have done in physics. So in physics, you send the cart down the ramp. When the cart is placed at the top of the ramp, it has gravitational potential energy. As you release the cart and the cart goes down the ramp, it increases its speed. Its potential energy is depleting and its kinetic energy is increasing, so that by the bottom of the ramp, it has zero potential energy, which I'm going to see if I can add in there. Zero potential energy. That's a highlighter. Oh well, we'll change to a pen. Okay, so that is energy that is changing form from potential to kinetic. We now want to do a very similar thing in chemistry, and we want to do it with chemical reactions. So in these next images here, you see a favorite graph of chemists. I talked about this a little bit in the Jamboard from last class, and what this is it's graphing potential energy as the reaction progresses. So what we have there is this arbitrary line right here represents the chemical potential energy. Sometimes this is referred to as bond energy. And some problems that I'm going to give you later, this might be labeled bond energy. See if we can get it in there. Okay, and it starts at some arbitrary level, and then what you do is you trace the so-called chemical potential energy or the bond energy as the reaction proceeds. So just like with the car at the top of the ramp, it starts with an amount of potential energy, and you follow that potential energy as the cart goes down the ramp. In that case, the potential energy depletes. In chemistry, it can go either way. Either the bond energy / chemical potential energy can increase or decrease, so we have to be prepared for those two scenarios. In the exothermic reaction, what happens there is energy is released from the bonds, and we feel that as heat energy. So the system warms. We feel the warmth coming out of that reaction, out of that explosion, if you will, if that's going to be your example exothermic reaction. But if this graph is about chemical potential energy, then what happens there is the chemical potential energy decreases during that. And that's the reaction that chemists call the exothermic reaction. But in chemistry, we have to be prepared for the alternative scenario. We're not talking about why this would happen, but we could start with the stored potential energy in the reactants at a certain arbitrary level. And then as the reaction proceeds, the chemical potential energy actually increases, going from the reactants to the products. And I'll label the reactants and products over here too. So we're not concerned with why that would happen. We just are acknowledging that it does happen. And our evidences for that are that it gets very cold. The surroundings get very cold. The classic reaction there is your cold pack. And that's because that reaction is being, as it proceeds, it's requiring energy from the surroundings. And so you're getting very cold as it takes energy from you to drive the chemical potential energy higher. Okay, so now we're going to shrink that, and we're going to slide this over, and I think, let's see how this is. All right, so what students are doing there is they're looking at evidences in the classroom. So you don't get to see chemical potential energy changing. What you do is you place a thermometer in your reaction vessel and you look at the changes as that reaction proceeds. Or you are perhaps feeling the side of the flask and you're saying, gosh, if this is what I'm experiencing, then that means that this is what the chemical potential energy was doing. So you have to indirectly produce these graphs. So I've got an example of each here. In this top one, what's happening there is as the reaction proceeds, so I've got a before and after, your thermometer increases. So I've got that both as the visual there, the thermometer increasing, and the person saying, wow, the temperature has increased. So what you then have to do is you have to deduce what's happening to the chemical potential energy. So if the thermometer is warmed, if the reaction vessel is warming, that means there's been a depletion of the bond energy or the chemical potential energy. So that means that in this reaction here, as the reaction proceeds, the chemical potential energy is decreasing. As a result of this chemical potential energy decreasing, you're experiencing that warmth. The energy is coming to warming the surroundings and warming you. And at the bottom here, the other situation is you just have your hands on the flask. And so in this particular scenario, you're touching that flask and you say, wow, that got really cold. So you then have to deduce what this chemical potential energy versus reaction progress graph will look like. And so what you deduce there is if you're getting cold, that energy is being removed from you. You're part of the surroundings. That energy is being removed from you, and that's helping to drive this reaction to a higher chemical potential energy. So if the energy stored in the bonds is actually higher in the products than it was in the reactants, where did that energy come from? Where did the energy come from to drive this uphill? Well, it came from you, and that's why you're experiencing the cold. So a lot of the questions are you have an observation from the classroom or from the chem lab, and then you deduce what this chemical potential energy reaction progress graph looks like. All right, we're at 6 minutes, so that's probably long enough. I'm going to back out of this. I feel like there was a third page, and yet I don't think I'm going to do it. You know what? I will do it. It's quick. Okay, so these graphs are similar. What they're looking to reinforce is something that you read about in an earlier class within the last day or two, and that's that to break bonds always requires energy. So you can see in both of these graphs, and I think I'll switch pen colors just for fun, they both have an upward arrow that talk about bonds being broken. That's because breaking bonds is an endothermic process. It requires energy. And then when new bonds are formed, that is an exothermic process, and energy is released. So those steps are always those steps. Breaking bonds is always endothermic. New bonds forming is always exothermic. But then the difference there is in the relative sizes of those arrows. So in the net exothermic reaction, in the overall exothermic reaction, I'll just write exo in here, that trended to have lower chemical potential energy. Sure, it had an up arrow step and it had a down arrow step, but overall, the reaction lost chemical potential energy. That's what makes it exothermic. Your hands get warmer, the thermometer in the reaction vessel increases. This one here, the overall equation, has an increase in chemical potential energy. That makes it endothermic. That means the thermometer dropped in temperature that was in the reaction vessel because that energy went into being stored in the bonds. So the temperature dropped in the vessel, and if you were holding that vessel, you'd feel that your hands get very cold. That's what drives the chemical potential energy up. Okay, so there's a lot in the YouTube videos and in the textbook reading and the practice problems that cover that. Thank you.